So thanks again for the invitation to present today. I'm really excited to talk to you all about different trends in poultry lighting, especially how it pertains to LEDs. Okay, and before I jump into the trends in poultry lighting, I did just want to take a minute to briefly introduce everyone to who Once by Signify really is. So Once is actually one of many brands owned by our parent company, Signify, and you'll probably actually recognize several of the different lighting brands that are under the Signify umbrella. So some of those include like Philips or the Philips Hue system or Wiz or Connect or Color Kinetics. So some of these are some pretty common household brands and residential brands that are sold by Signify. But Signify extends into a lot of different brands, including technology brands, specialty brands, regional brands, and even some value brands as well. And Once by Signify falls under the specialty brands. And even further, we fall into our agricultural division that's separated out into a few different brands depending on the industry. So for our animal lighting solutions, the Once brand is focused on poultry, swine, and a little bit of aquaculture. And we also share the aquaculture space with some of our Philips branded products. And then extending out beyond animals even, we also sell lighting solutions for horticulture under the Philips brand. And recently we've even started selling lighting solutions for cannabis under the Fluence brand. Okay, so now we can switch back into trends in poultry lighting. And I first wanted to start with, kind of defining what light is. And at its core, light is electromagnetic radiation that can be perceived by an organism. So for poultry, this is between 315 and 750 nanometers. And for humans, this is between 400 and 700 nanometers. And when we're talking about nanometers, we're actually talking about that's what the wavelength is. So when people refer to shorter wavelengths, we would be referring to something like 400 nanometers, and longer wavelengths would be closer to 700 nanometers. And so the shorter wavelengths you get, typically the more bluer the light is perceived. So, if we're referring to 400, that's going to be a very blue light versus 700. And as we get longer in the wavelength, we're going to get into the red portion of the light spectrum. But lighting can vary in many aspects other than just color or spectrum. So we can look at how light varies based on schedule or photoperiod, distribution, and intensity. And when we think about how we're going to light a type of environment, and especially environments that are made for poultry who are very photosensitive, as you've heard about already, we really need to consider how each of these different lighting characteristics and how they interact with each other to create the most relevant lighting solution for that particular species, and also to examine the different dynamics of how these are all working together to create that optimal light spectrum. And we need lighting that's specifically made for poultry because, like you've heard for the previous two speakers, they do perceive light much differently than humans. And for most of my presentation, I'm focusing on chickens, but the same is true for ducks and turkeys. And so because our spectral sensitivities are much different than avian species in general, our color and intensity perceptions are going to be quite different. And as you heard from Greg, poultry are considered tetrachromatic, meaning they perceive a broader portion of the light spectrum because they have 4 cone species in their retinas that are responsible for perceiving that light color, versus humans, which are tetrachromatic, meaning we only have 3 different kinds of cone photoreceptors. And so that extra cone photoreceptor for poultry is ultraviolet sensitive. So you can see that's why they have this little bump down here past the blue portion of the spectrum, which is all that we're able to perceive. So they're able to perceive this other element of color that we're not even capable of perceiving, which is pretty neat. And then poultry also have these oil droplets, which I think Greg also pointed out in one of his diagrams, that are present on the cone photoreceptors for poultry, but not on human cone photoreceptors. And this gives them increased accuracy for color discrimination compared to species that don't have those oil droplets. And so what all of this ultimately means is that the lighting that's optimal for humans may not necessarily be what's optimal for the chicken. So we really have to start thinking about what are they seeing and how are they registering that visual information under certain lighting conditions in order to provide the most optimal environment lighting wise for them. And so again, this has already been covered a little bit, but poultry actually perceive light in two different ways. One is visually through these cones and rods, and this gives them the capacity to respond to their environment, facilitate sight, search for food, establish pecking orders. But they also have this non-visual photoreception through these extraretinal photoreceptors in the brain. So like in the pineal gland and the hypothalamus and some other areas of the brain as well. And these have direct control over many physiological processes and really are able to mediate some of those different hormonal cycles that are involved with those processes to stimulate different behaviors and responses within the bird. So this includes like melatonin cycling, which can ultimately lead to circadian entrainment and how reproductive behaviors are expressed in our egg-laying species especially, but it can go back to mating, fertility, egg-laying time, egg-laying persistency, lots and lots of reproductive behaviors, and also metabolic regulation and immune response as well. And what we've seen in previous studies is that in addition to photoperiod being obviously one of the most primary aspects of determining photostimulation for birds in general, when we're talking about spectrum, red light penetrates the most effectively through the layers of tissue, skin, bone, to reach these extraretinal photoreceptors in the brain for poultry. So especially for our egg-laying species, this is really important to incorporate a portion of the red spectrum into their overall light environment in order to maintain those circadian rhythms and improve egg production and to make sure that those reproductive behaviors are actually being elicited. And so we often get this question as a lighting company of why should we not be just using sunlight? And there's a lot of reasons for that, but the main one is that natural lighting, when we think about, just day to day and maybe even like minute by minute, natural light is not always optimal. It's not always static. So there's changes in the weather that can influence the light spectrum. So even just a cloud passing over the sun can change the dynamics of that lighting, the intensity, the spectrum. And seasonal changes can have large variations on light intensity as well. So think about like winter versus summer. Our day lengths are much different then. We're gonna have shorter day lengths in the winter and much, much longer day lengths in the summer, depending on your location. And like Greg was alluding to earlier, in the wild, the red jungle fowl, which is the predecessor of the chicken, the domestic chicken, is living in a much different environment than what we're raising a typical broiler chicken in today. So the red jungle fowl's environment was much more filtered and dimmer because light is coming through this tree canopy. So the spectral qualities and the intensity of that light are going to be much different than just direct sunlight. And so ultimately, artificial light is not dependent on nature, and it's completely controllable. And when we think about what factors we need to include in our poultry houses, we want things that we're able to control. So while we don't want to bring sunlight necessarily into our houses as the primary source of artificial or the primary source of light, we do want to take inspiration from it and integrate that into new technology and innovations to create an optimal environment for our birds without sacrificing the control that we have over that environment. So when we start thinking about artificial lighting, what do we need to look for and what should it do for us? So I've kind of made three different general points here. The first one being that it needs to be sustainable and controllable. Obviously, we need a bulb that lasts a long time. So we need to consider bulb longevity. We need to have a bulb that is low energy consumption. or consuming less energy, and it needs to be dimmable. And we also need it to improve overall bird performance. So for broilers, that could be improving feed conversion and growth. And for maybe our egg-laying species, that could be maintaining the persistency of lay or maintaining fertility. And of course, we wanted to enhance bird welfare. So reducing stress and fear responses, creating an environment they are more comfortable in. It's a pretty anthropomorphic term, but it's something that they are able to spend time in. And this is true not only for poultry, but also for their human caretakers as well. We need to have an overall positive lighting environment for the birds and the growers. So throughout time, many different sources of artificial light have been used in poultry houses, and two of the main ones that have been popular over previous years have been incandescents and compact fluorescence, or CFLs. So on this slide, you're going to see the spectral curve for each of these two different types of lighting, and you'll notice some pretty large differences in the overall output. And this difference in light output depends on how the light is generated in each different lighting type. So for incandescents, an electric current is passed through a thin metal filament, that's usually like tungsten, and that filament is heated until it glows and produces light. So we think about like a fire, it's putting out a lot of heat, it's burning, and we're getting, like Greg was saying, this really red spectrum. So it's very warm, it's a very warm spectral output, which may be good for like a breeding species, but there's a lot of disadvantages to incandescents, like they have a short lifespan, and they're not very energy efficient because, again, when you think about something that's burning, it's putting off a lot of heat generally, and the same is true for incandescents. So a lot of that energy that's put into the bulb is lost as heat. So it's not a very efficient light in general, about 16 lumens per watt. And then for compact fluorescence, an electric current is driven through a tube that has different gases in it. So typically like argon and mercury are two that are in that light. And then this generates an ultraviolet light, and that ultraviolet light is converted to visible light by a phosphor coating on the inside of the tube. So the great thing about compact fluorescence is we do have more spectral options than we did with incandescents. There's warm spectra, there's cool spectra, but they are very challenging to dim, and they're only a little bit more efficient energy-wise compared to an incandescent, so like 50 to 70 lumens per watt. But LEDs, especially over the last like 20 years, have become this go-to artificial light source for poultry houses. And this is true for a number of reasons. The poultry-specific bulbs that are available, or the luminaires that are available, are highly efficient. So usually we target above 100 lumens per watt for a poultry-specific LED. So a lot of them are around 110. And these are great because they're not burning anything, so we're not generating a lot of heat. And they have a lot of spectral tunability, so they can come in a broad range of colors. And they have a much longer lifetime than the CFLs or the incandescents. They're also pretty easy to dim and to modulate. And over time, there's been a lot of technological advancements. So this includes species-specific options, but there's also been a lot of interest in spectral tunability and even wireless connectivity. So kind of like what we did for light in general, I did want to define what light or what LEDs actually are and how they work. So unlike other light sources, LEDs don't use heat or gases to create light. They're actually using semiconducting materials that produce light and color. And many of those materials are based off of gallium. And the layers of the semiconductor are doped with chemical impurities to create these two layers that you see here. So there's the N-type layer that has a bunch of electrons, and the P-type layer that has electron holes. And when a current is applied, those electrons in the N-type layer fall into the holes of the P-type layer. And as those electrons fall into the holes, they release energy in the form of light. And so this migration of electrons from that N-type layer to the P-type layer is called LED epitaxy. And one of the most valuable advantages of using LEDs is that we're able to use this epitaxy along with different semiconducting materials and different levels of chemical impurities to create different energy gaps between those two layers, the N-type and the P-type layer. And by doing this, we're able to modify what color of light is being emitted from the LEDs. So if you think way back to before 1989, a lot of the LEDs that we were seeing were indicator lights on remotes or in calculators, and most of these were either red or green LEDs. And the reason for this was because blue technology was more challenging to create than red and green LEDs because it required a higher energy gap than what we were able to achieve at the time than what was required for green or red LEDs. So we just didn't have the technology to create that energy gap that was capable of producing blue light. But they were able to do that in 1989. And since then, with the creation of blue LEDs, we've really been able to generate a much broader range of spectral outputs, and it's actually increased the ability to create white light, which has helped expand LEDs into a bunch of different markets, but it's been especially helpful for the poultry industry. And so once we had these blue LEDs, we were able to create different variations of white LED because we were able to use phosphors to absorb short wavelength light to emit a longer, broader wavelength spectra. So that blue light was really the missing link that we needed to have that short wavelength to then generate something that was longer and broader. And there's a few different phosphors that can be used to create various temperatures of white light or even other colors like green light. And since we're able to do this and we have some spectral flexibility, even in the different temperatures of white that we're able to create or different colors, we have a lot of spectral flexibility, which is very important to poultry because we're able to tune that spectrum depending on the species. And so kind of like how Karen and Greg were mentioning earlier, there's been a lot of research that shows that light spectrum is really impactful on performance and welfare. So on a layer and breeder side, we really focus on including red in the spectrum. And it's been demonstrated that red light is required to stimulate the reproductive axis. And it's also been proved to improve laying performance in general. And when we talk about adding red into like a white light, for example, to create a red enhanced white light, we show that this can reduce physiological indicators of stress compared to like a typical white 3000 Kelvin light. And on the broiler and pullet side, it's a little bit different. So I'll just put all of those up there. But we actually focus more on the opposite end of the spectrum. So we're looking at like the blue and green portion of the spectrum. So there's been many studies that show that blue and green light promote muscle growth that result in increased overall growth and performance, and that green light accelerates muscle growth and stimulates growth at an early age. And then if we transition to blue light later in life, we can stimulate growth in older birds. And overall, we know that blue light reduces the behavioral fear response and physiological indicators of stress in broilers compared to a white light. And when we talk about monochromatic light, we can also use different spectral extremes as tools for bird management. So for monochromatic red, for example, we can use this as a tool for mitigating severe feather picking and cannibalistic behaviors in layers and breeders, since that red light, that monochromatic red light, will wash out the appearance of wounds and blood that are oftentimes really attractive to birds when they get into that habit of cannibalistic behaviors. And so this gives the wounds some time to heal, and then we can ultimately return them back to their regular lighting program and the regular spectrum. And ultimately those birds will stop feather picking as long as the stimulus is gone. And then kind of shifting over to like a monochromatic blue light, we can also use this as a tool, but it's used as a calming tool for most poultry species, except ducks. We can't use blue light on ducks. But for chickens, monochromatic blue light is really great because we can keep it at a very dim intensity and use it to keep the birds very calm and inactive during certain intensive handling procedures, whether that's catching, vaccination, or loadout. So we've had great feedback from even like cage-free laying hen houses that have used monochromatic blue in one of our dynamic lighting solutions to catch their layers, and it keeps them much calmer than a typical catching scenario would be for them. Okay, so now I'm going to switch gears a little bit and discuss light intensity modulation, or more simply known as dimming. And this has also been touched on in the previous talks, but I think it is a really important topic of, why do we need to control light intensity in poultry houses? And I'll focus more on layers here, but some of this is relevant to broilers and other species as well. But we need these dawn and dusk periods, especially, to provide a really gradual transition between the light and the dark. And if we think about poultry houses and poultry in general, this is really important because poultry in general do not like a lot of instant change. It really stresses them out. And like Karen was saying, there's a lot of vocalizations, a lot of wing flapping, a lot of piling even sometimes. So providing those gradual transitions is really important to kind of ease them into different lighting environments. And then we can also use that as a signal for beginning and ending the day. So we need to include that in our photo period. It reduces stress after lights off, and it also reduces stress as the lights are coming on. And what's really interesting with dawn and dusk cycles in especially like cage-free layer systems is that we can modify the dimming sequences of different areas in the aviary system to stimulate bird movement around the system. So for example, in this picture, birds in general want to go and roost in trees, and the same is kind of true with our layers too. They want to get up high and find a perch to settle in for the night usually. So we can dim certain areas of their system in an order to get them to move up into the system to find the perches where we want them to be in the system for the night. If we don't do a dusk dimming and we just shut the lights off with no dawn or dusk, no rhyme or reason, a lot of those birds will stay on the floor, and there's an increased likelihood that they will wake up on the floor and then lay their eggs on the floor, which is something that we always want to avoid. And in general, modulating light intensity during the day can help keep birds calm. So we want to have the ability to adjust that spectrum or the intensity no matter what time it is. But during the day, we want to keep the birds nice and calm. And in addition to being able to control the light intensity, we also need to understand, what measures are representative of how poultry perceive that intensity. So especially with poultry-specific LEDs, we want to make sure that we're understanding how they're perceiving that intensity. So typically lux or foot candles is used as a measure of intensity in the field, but these measures are actually based off of the human spectral sensitivity curve and not necessarily on poultry. So the lux values that we're using, or the foot candle values that we're using, aren't completely accurate for measuring the intensity that poultry perceive, because their sensitivity curve is not identical to humans. So this is where that adapted measure of intensity, the Galilux or Clux, is used to provide a more accurate measure of poultry perceived light intensity. And Clux is especially useful when we're measuring the intensity of poultry-specific LEDs, because a lot of the times these are including peaks of or wavelengths that are in either the blue portion of the spectrum or the red portion of the spectrum, and can ultimately affect how the poultry are perceiving that light output. So you'll see, just for example, here's a bunch of different types of artificial lighting, ranging from incandescents all the way up to generic LEDs. And you'll notice there is quite a bit of difference between the Clux values and the lux values. But this difference really is more pronounced when we start modifying the spectrum in a way that is targeted towards different poultry species. So we can get up to, like an 83% difference just by modifying what that spectrum is doing. And regardless of what intensity we need the lights to be at, we have to have a good way to control the intensity that the lights are set at any given point. And while there's multiple ways that we can modulate artificial light, the most effective way for LEDs is to use pulse width modulation, or PWM. So PWM controls average current and voltage delivered to the LED by rapidly turning the LED on and off. And this provides a really precise output level from the lights, and it's really ideally suited for applications needing to maintain specific characteristics of an LED. So for example, like efficiency or color or temperature. And when we think about poultry specific lighting, we definitely don't want lights that are changing color randomly. There's times where changing color is a good thing, but based on your PWM, you really don't want color flicker changes in those lights at all. So it's really important to maintain the settings that we program the lights to be at, and PWM provides a great way of doing that. And we're also able to dim the lights in over a more broad range. So we can get down to like 0.01% light intensity, 100 to 0.01% with PWM. And that's exactly what we need for poultry, because like we were saying before, we want to make sure that those lights are gradually turning on. We don't want them to just go from 0 to 10% intensity. We want them to start at 0 and get up to 100% or wherever they're supposed to be. So there are other dimming methods like constant current reduction that have minimum thresholds for the minimum intensity that the lights can be at, or the minimum dimming percent that they can be at. And those just aren't as effective in getting down into the deeper dimming that we need for poultry. And so with PWM, it sometimes raises some concerns about flicker. And so I did want to have a little discussion about flicker, which is also known as temporal light modulation, or TLM. And when we're talking about flicker or TLM, we are describing changes in the light output over time. So it's an unsteady or intermittent change in the light spectra, or in the light intensity or spectrum. And we use the frequency of the change in the light output to determine the type of flicker or TLM that we're dealing with. But TLM is not just limited to dimmers. There are many ways that we can experience TLMs outside of just artificial lighting. So intensity and spectrum of light changes throughout the day. So those can be considered TLMs. So we have like a much cooler spectrum during the noon hour. And then we also have a warmer spectrum during like our dawn and dusk periods. And the intensity also changes over the course of the day as well. So those are all TLMs. We also can have variation in light intensity in tree canopies. So if you're under a tree canopy, there's going to be brighter spots, there's going to be darker spots, and those are all considered TLMs. And then we can also have just momentary TLMs, like objects flying over the sun, like this hawk, to create momentary changes in intensity and spectrum in certain areas. So before I go to the next slides, I do have like some flashing things here. So if you see that, just if you're sensitive to that, just turn away for a second. So there are certain ranges of TLM that can lead to health effects in poultry, or in humans, sorry. So this includes like migraines, eye strain, fatigue, blurred vision. There's panic attacks, increased heart rates, photoepilepsy. So we really have to pay attention to this, even just from a human welfare perspective, because we don't want people to deal with epileptic episodes when they walk into a poultry house. And so to avoid these issues with flicker in humans and poultry, we need to identify the critical fusion frequency, or the CFF. And what the critical fusion frequency is the frequency at which a regularly occurring change in light stimuli is perceived as steady. So that frequency is measured in hertz. And for example, with humans, our CFF is between, neurotypical humans are around 60% or 60 hertz, but it can be anywhere between 60 and 80 hertz. And what you'll see is you can perceive the flicker of this 0.5 hertz and this 2 hertz flicker on the screen, but you can't see probably any flicker in the 60 hertz frequency flicker. And that's because that's our CFF. So the flicker, so the light is still flickering, but we just can't see it because those, the different periods that are causing that flicker to occur are so close together. They're happening so close together that we can't see it and can't visually perceive it. So a lot of our computer monitors are using 60 hertz. So anything past 60 hertz is really not perceived as flicker by humans typically. And the critical fusion frequencies for birds can vary depending on species and illuminance. So birds, for example, there was a paper that was done showing that birds that hunt fast flying insects have higher CFFs than those that hunt slower moving insects. And we know that chickens have a relatively low CFF compared to other species like falcons and other species as well. And there are some questions that have been brought up about the effects of temporal light modulation on poultry. And when we think about the CFF of birds compared to humans, we know that the critical fusion frequency for chickens is higher than humans. So several studies have used some behavioral methods to assess CFF, and all have reported CFFs in the range of 75 to 87 hertz, with some studies showing that there are behavioral responses to higher frequencies, but only in brighter light intensities like 100 lux plus. And like with humans, flicker may negatively impact birds, but we haven't seen a lot of studies that have yielded consistent results. So for layers, the frequency of light above 100 hertz didn't have an influence on the accuracy of jumps between perches. And then Karen was mentioning earlier that her lab has come out with some interesting studies lately on flicker frequency in layer pullets and laying hens, and also on turkey hens. And they found a minimal impact of flicker frequency on pullets in the rearing stage, and then none of the impacts that they did see translated over into the layer stage with those same birds. And then visible flicker also had minor negative impacts on turkey hens, but that all occurred in early life in that study. And temporal light modulations are measured in a few different ways. So frequency or hertz is one that we've been talking about, and that is just essentially how fast the modulation is moving. And this does account for most of the biological effects of flicker and of perceptible flicker. And our acceptable limit for poultry is greater than 100 hertz. So like, for example, all One's products are 100 hertz or 120 hertz and above. There's also some other measures of flicker that are sometimes published in papers like flicker index or flicker percent. But these are actually insufficient for explaining biological effects of flicker on any poultry species and humans as well, because it's really just looking at what the differences between the high and the low states of that waveform. So it's actually not really applicable to determining how any organism is perceiving flicker. It's just looking at certain factors involved in just the shape of the waveform, essentially. But there are some more complex metrics that do account for all of the biological effects that are influencing human perception. So for humans, that would be PST-LM, which factors in the frequency, the flicker index, and the waveform. And our acceptable limit for that is anything that's less than or equal to 1. And 1 would mean like the average observer has a 50% probability of detecting flicker. And then there's more recently a metric for avian flicker visibility that is based off of the same equations and general concepts of PST-LM that is used, that was modified for poultry light sensitivity. And so that factors in frequency, flicker index, and waveform as well. but this accounts for all the factors influencing bird perception. And again, we want a value of less than or equal to 1 for that metric as well. And so we at once have a light meter that we have developed recently that does have the ability to measure avian flicker visibility metrics and also clucks. There are other meters that measure clucks, but ours is the only light meter that will measure both of these metrics together. And there really is a strong need. You know, we have all of these different metrics for measuring flicker and for measuring intensity, but there really is a strong need to develop more robust species-specific metrics and sensors for a lot of different measurements that could be included in intensity, in spectrometers and different light meters. So, for example, illuminance, like refining chicken lux is a good opportunity, and also figuring out the visual sensitivity curves of other species and then integrating those into different spectral meters would be very interesting. Looking at color rendering index, we know the CRI for humans, we have a scale for that, but we do know that poultry perceive color much differently than humans, and we don't really have a good way to measure that. So having a color rendering index measurement would be, that was poultry specific, would be really great. For circadian impact, we also have a measure for that in humans. It's called melanoptic lux, and that's the illuminance that affects the circadian rhythm. And we don't necessarily have a metric for poultry yet, so something along those lines would be interesting as well. And then also identifying other metrics of flicker sensibility or sensitivity for other types of flicker, like stroboscopic flicker, which is a different form of flicker than what we are defining as flicker here. Okay, and then last shift is going to be into advancements in LED technology for poultry. And the first one that I want to talk about is advancements in LED ingress protection. So like everything else in a poultry house, we need the housing around LEDs to be barn proof or robust enough to withstand the chemistry of the barn and all of the abuse that they'll probably go under when they're in a chicken house. And we need to keep the electrical components in life safe from water and dust ingress. So the IEC, which is the International Electrotechnical Commission, has developed ingress protection or IP ratings that grade the resistance of an enclosure against the inclusion of dust and liquids. And this rating system has been really widely adopted throughout the industry. A lot of different lighting companies use it. And the rating consists of 2 numerals. So the first indicates the resistance to the light housing resistance to solid objects like dust. And the second numeral indicates resistance to water ingress. So there's a scale, and you can look it up. It's on the IEC webpage as well, if you're interested in reading more about it. But all the lights in poultry houses, we recommend that they be IP65 or higher, which means that they are dust tight. So there's no ingress of dust. And we want them to be protected against low pressure water jets in any direction. And we've also talked about this a little bit in the Q&A session for Karen's talk, but gradient lighting has really been gaining traction in the broiler industry, and it's a super interesting concept. So when we're talking about gradient lighting or variable lighting, we're defining that as a light that provides predefined areas of high intensity light. So in most cases, this is under the feed lines, and then that high intensity light gradually dissipates out into areas of low intensity light. So the birds, like Karen was talking about, have this choice between which intensity they can be under. So they can go and sleep over here, and they can eat over here, and they can do whatever they want in the middle over here. So it's a little bit different light distribution than what we're used to seeing, which is more of a highly uniform lighting system that's hung on the ceiling. So there was a study that came out in 2023, I think in February, out of the University of Arkansas that compared ceiling lighting, natural sunlight, lighting and gradient lighting sources that were mounted on the feed lines in commercial houses. And they were examining the performance and welfare benefits of gradient lighting in those commercial settings. And so they found that compared to ceiling lighting and natural lighting, these gradient or variable lighting sources had several performance and welfare benefits, including improved feed conversion by 1 to 4 points, and then a lot of positive impacts on different welfare indicators. So there's a bunch there. Reduced litter moisture, reduced foot pad lesions, reduced leg problem cold birds at day 49, increased activity and dust bathing behaviors. So this is kind of linking back to that expression of natural behaviors, which is always what we want to see in birds. And they also saw reduced fear responses and reduced gene expression levels of TPH2, which is a rate-limiting enzyme of serotonin biosynthesis, which also indicated reduced stress in these birds under the gradient lighting system. And overall, what they concluded was that broilers that were in this gradient lighting system may have been more comfortable, where they had this choice of what intensity they wanted to be under throughout the day. So they weren't necessarily forced to be in this super low light intensity, and they weren't forced to be in the super high light intensity. So having that choice was beneficial both performance-wise and welfare-wise. And so here's another close-up view of what those lights look like. So this is our model of the gradient lighting, but it sits above the feed line. Actually, our model sits above the feed line, and you would think, well, there's going to be shadowing there, but there's not, because we've designed the placement of the LED chips themselves and the shape of the lens to bend light around that feed line. So we're actually reducing any potential shadowing from like a bird walking underneath it, or even like shadowing from the equipment itself. So it's a really interesting concept and a pretty neat product. And then the last little bit of technology I wanted to discuss today was the wireless control systems that have been emerging as a more flexible alternative to like the hardwired traditional control systems that we have in poultry houses today. So there are systems available like this one shown here. And like if you think about it from a residential lighting solution perspective, it's very similar to the Philips Hue system, where an app is used to upload lighting commands from a central hub or to a central hub or gateway. And then that gateway has wireless communication to each individual light. So it's constantly sending the lighting commands from your light recipe or your light program to those lights to make them do whatever you need to do. So that box there just basically replaces a dimmer in most cases. So the gateway is essentially talking with the lights, and the lights are also talking to themselves. So it's a very dynamic solution, just in the sense of how we control it. And we make it, it can be even cooler when we integrate that communication system with multi-channel LED luminaires. And then we can do some really amazing things with the system. So we can have full control over an almost limitless number of spectral combinations, light programming capabilities, and even like zoning capabilities in the house can be flexible when you have this wireless mesh network with the lights. So, you know, for example, we can zone them out based on their power line, which is pretty typical of, you know, like a standard system, but we can also change that if we wanted to. We could have, you know, a quarter of the lights on one corner of the house and another quarter of the lights on the other corner of the house in one zone. And we can change that again if we wanted to. So it's not limited to these power lines like we're used to seeing, or to your electric configurations in the house. So we can run different recipes and different colors. Obviously, no broiler house would ever be this colorful, but we can do some really interesting and integrative things with the system when we pair the wireless communication with those multispectral luminaires. Okay, and that's really all I had, but just some quick take-home messages for everyone, because I know that was a lot of content to breeze through. Artificial lighting in poultry houses, it has to be sustainable. We have to improve bird performance, and we have to enhance animal welfare. And while many options for artificial lighting are on the market, poultry-specific LEDs designed to perform in barn environments and meet the visual needs of poultry are really the most effective option that's available at the moment. And how we measure and modulate light intensity in those poultry-specific LEDs is really important from both a bird and a human perspective. We want to measure flicker in a biologically relevant way that is going to be beneficial for both species. So we can look at frequency, we can look at avian flicker visibility metric, we can look at PSTLM for humans, but flicker index and flicker percent really aren't going to tell us much about the lights. So we really need to focus on things that are going to be biologically relevant to all of those different species. And there's also a need to for future development for many different metrics for poultry specific lighting, whether that's melanopic lux or chicken lux, or maybe even like a turkey lux or a duck lux, who knows. But we need more refined metrics that are less focused on human spectral sensitivity and more focused on poultry visual sensitivity. And then, of course, there are a lot of products available on the market today, and some of those even have advancements with various lighting dynamics that can really change the game for the poultry industry as a whole and create a really dynamic solution that can integrate a lot of those different lighting characteristics that we talked about into one product. All right, and that is officially the end of my talk.